Okay, and we're live. So, first of all, good morning and good afternoon, everyone. It is a pleasure to welcome with us Professor Rita Singh. She is presenting for us a talk, a lecture, which is part of the ISCA Distinguished Lecture Series, the DLP program from ISCA. And this is also a lecture of our dear informatics seminar. Professor Rita Singh, who is here with us, she's from the Carnegie Mellon University. She works at the Language Technologies Institute at the Carnegie Mellon University. And her work spans voice forensics, human-centered AI, and sound, the science of sound itself, let's say. In recent years, her research has had important implications for security, ethics, and the future of biometric technologies. Her talk is entitled Human Voice as a Biometric. Can generative AI systems really emulate it? So Professor Rita Singh, thank you very much for being here with us. The floor is yours.
Thank you. Good afternoon, everyone, and thank you very much for being here. It's indeed a pleasure to be talking to you. In my lecture today, I am going to examine the human voice as a biometric. And we are going to talk about how generative AI systems emulate human voices and whether those voices are really as realistic as we think they are. Now, I only have 50 minutes or so for this presentation. So the lecture, and I have to cover a lot of topics. So it is going to be cover the topics that I want to cover in a very broad sense. I will not be going deep into any one topic. So before I begin, though, I do want to mention, as Matthias did, that this lecture is a part of the ISCA, which stands for the International Speech Communication Association lecture series for 2025. ISCA was founded in 1989, and as we all know, it is globally one of the two main organizations for speech communication, science and technology. The other association is IEEE Signal Processing Society. So, okay, let's begin. Now, let's talk about biometrics. Any entity that can be used to infer information about you, about the bioparameters of a person, is a biometric. We all agree, right? Now, in order for an entity to be a biometric, it doesn't have to be unique. However, it has to be unique to be a biometric identifier. So let me begin with this question. And please feel free to answer, use your voice, answer. It's getting recorded, but that's fine. Do many people in the world have the same fingerprints?
I wouldn't think so. I hope not.
You hope not, right? Okay. Here's the reality. The chances of two people having the same fingerprint is 1 in 54 million, according to Galton. No one really knows. No one has really proved that fingerprints are unique. In fact, in a very recent incident, in the Madrid train bombings, there's a set of fingerprints found that matched the fingerprints of a US citizen exactly. So there you go. It has never been proven that fingerprints are unique. Another question, do many people in the world have the same face? What do you say?
I would say that it depends on how you evaluate the face. If you talk about key points, many of them will have the same key points, I think, in my opinion. But okay. It depends on how you see it. Yeah.
That's a very scientific answer. That's a very good answer. Thank you. Here's the reality. The incidence of identical twins is about 1 in 250 births. And we all know that identical twins look alike, right? And this occurs randomly. It's relatively consistent worldwide. It is independent of factors such as age, race, or genetics. It is what it is, 1 in 250 births. What about DNA? The chances of two people having the same DNA are the same as the chances of being an identical twin, 1 in 250. So while we think that DNA is unique to an individual, in reality, it is not, right? Now let's get to voice. Do many people in the world have the same voice? Think about it. I think everyone is going to say yes. We've heard so many people who sound alike. The voices are not so different across the world and so on and so forth. Okay. That's what everyone thinks. Let's find out. And the first way to find out is let's use some subjective estimates. Okay. How many different types of voices do humans have? No one has actually counted, but people have tried to categorize voices into a small number of categories in the context of different fields of its use. Okay, so if we talk about music and drama, they have been roughly categorized into a few categories. And here's an example of different voices. They sound very nice together.
There once was a ship that put to sea. The name of the ship was the Billy of Tea. The winds blew up her bow, it down, oh blow, my bully boys blow. Soon may the weatherman come to bring us sugar and tea and rum. One day when the tonguing is done, we'll take our leave and go.
All their voices were different, musically speaking. So let's say possible voice types are 6. Probably not. There are a few more categories here. So here are some common categorizations from the field of music and drama. And I'll play them out one by one. These are not the only ones, but these are the key ones. I may be missing 1 or 2 in these. Let's see where we are going with this. These samples are taken from the Royal Opera in the United Kingdom. So first, a bass voice. A baritone. Tenor.
Amici sono qui, amici sono qui.
A mezzo soprano. Here's a soprano. Okay, and interestingly, this is a countertenor.
You know I'm a countertenor, right? Literally the opposite of a bass, right?
Okay, so 6 possible types, perhaps a few more, 2 or 3. Let's look at other subjective categorizations. Okay, this time let's include all people, not just people who can sing. So in another set of subjective categorizations, and these are based on the perceived flavor or the sound of voice, there are many named out there, but 24 out of a possible 120 types of voices from a flavor perspective have been described in the scientific literature, and they have been used as a basis for multiple studies. And these are labeled as shown here on the slide. There are 24. Can you see my cursor?
Yes, we can see your cursor. Don't worry. Yeah.
Okay. So there are 24 of these, which are very widely used in the scientific literature. So let's say there are 24 different voice types based on a categorization of their flavor. Okay. Now let's set that aside. There are 2 genders conservatively, and the voices of the 2 genders are different, as we know. 3 ages. right? Let's conservatively say that we can divide voice types into three age groups: children, young people, and old people. Okay, these are very rough categorizations, and everything that I'm talking about is based on subjective evaluations or our subjective observations. And so these are what we perceive as voices. Here's another set of subjective categorization, and this is based on what are called the Laban efforts. The Laban efforts are named after Rudolf Laban, and they categorize, this categorization is based on the style or the interplay of intensity of the voice and the cadence. So there are three sets of possibilities: sudden, sustained, direct, indirect, light, and strong. And so there are 2 to the power 3, 8 combinations possible of these 3 different sets of characterizations. So, and the 8 of them are listed here on the right. They are labeled on the left here, and I'm going to show you some examples of dabbing, pressing, and floating, just to give you an idea.
Short, sharp, sudden words. He chops them up and pushes them out one by one, as if he's poking as he's speaking. So that's dabbing. You can have pressing, which is strong, sustained, and direct. If you are speaking directly and sustained and strong. Notice I've not really changed my accent throughout these. I'm still just speaking really in my own dialect. Let's try floating now. So floating is light and sustained but indirect. It can be all over and it doesn't really know where it's going. It's also sustained but indirect and a little floaty.
You might say these are just stylistic differences, but they do count. They do change the flavor of the voice. Now let's keep going. Okay, how many countries are there on Earth as of 2024? So the answer is 193 or 197, and why that is so is in the yellow box on the right, bottom right. We won't go into that. Depending on different recognition criteria, there are 193 or 192 or 197 countries. Now, my question is, if everyone spoke English as a second language in each one of these countries, would the accent within each country be different? Remember, my question includes English as a second language. So I think everyone's answer would be yes, the accent would be different. Let's make a gross simplification. Let's assume that we have only one language, English, and we have only 50 different accents of it. And by one language, I mean one language that is spoken as a second language. And we have 50 different accents of it. And I picked the number 50 because on the slide, you'll see listed the 50 different accents of English that are well recognized by the linguistic community. Every language is different, and if you habitually speak a first language with all its nuances, it leads to habitual articulation differences, which leads to differences in the sound of your voice. So it matters. Articulation differences matter. Okay, so let's say there are 50 different accents of English, and let's do some calculation. So far, with everything that we have considered, 24 different voice qualities. Let us start with the 24 different voice qualities. We are going to assume that only 3 of the 24 voice qualities matter in actively defining the perceived sound of a person's voice at any time. And so the possible voice types is 24 choose 3, which is 2024. And then if we take gender and age and effort into account, the possible voice types can be calculated as 97,152. And then we take the articulation differences that I just mentioned into account, 50 of those, which is a very conservative number. We have something like 4.8 million different kinds of voices. But that's still a small number. The population of the Earth as of October 2024 was estimated to be 8.1 billion. right? So these numbers don't tell us that the human voice is unique. That's not what they indicate, right? So if I ask you the question again, do many people in the world have the same voice? Probably your answer is not going to change. You're still going to say, maybe, yeah, they do have the same voice. But let's keep going. This time, let us base our calculations on objective measures, okay? Now, voice or any sound wave, for that matter, is a pressure wave, okay? Here's an example of a frog creating a pressure wave by emitting a sound. You can see the pressure wave impressions in the water, right? Now, here is a pure tone. And this is a 400 hertz tone. This is what it sounds like. If it's an infinite sine wave, then its spectrogram will just have one line on it temporally extending to infinity at 400 hertz, right? Now, if it were not an infinite sine wave, then we know that there would be harmonics in the spectrogram, right? So here is the same tone, 400 hertz tone, that is modified by a modulation frequency of 10 hertz. It is modulated. And here's what it sounds like, right? And if we look at the spectrogram, it is going to have harmonics. Right now, it's not at a resolution where you can actually see it. But here's actually, I misspoke there. If it is not infinite, you're going to see harmonics. Now, here is the spectrogram of the frog's tone. And you can see the harmonic structure in the spectrogram, right? So let's examine the human voice in comparison. Here is a spectrogram of this.
Popeye the Sailor Man. Popeye the Sailor Man.
It's an old song. So what you see here are very complex modulation patterns, very complex changes in harmonic structure temporally, and there are other complexities from a signal processing perspective. And we are going to base our calculations on measurements of these complexities. It stands to reason that we should, because many of these are independently connected to our vocal production mechanism. So from the physics of voice production alone, there are about 44 independent entities that can be measured from the voice signal. And by independent, I mean the value of these entities is a primary control parameter in the speech production process. Okay, so these metrics cannot be, they are independent, they cannot be deduced from one another or from other things that you can measure from the signal. And some examples of these 44 independent entities are given on the right here in this list. Not all of them are given. And this is on the right in the box is a set of entities that most audio processing systems toolkits out there extract by way of features from voice. They're not independent. Not all of them are independent. A lot of redundant information is being extracted there. But anyway, let's go on with our estimate. So remember that each of these values is continuous. So each measurable entity or each feature has a continuous range of values. And the range of value is likely a bounded range for each of these entities. However, the interesting part is that the range of variation of the human voice has never been mapped. So we don't know these ranges, but we can still do some rough calculations. So one simplifying assumption that we can make is that we can assume that the range of each entity is quantized to only a few levels, only k levels. For example, if k equals 2, we could quantize the range into low and high. For k equals 3, it would be low, medium, and high, and so on and so forth. And then when we do the calculations, here is a table ultimately that shows the collision probabilities. And here the last column is important. So here, so let's begin with let me explain what this is. So Q stands for the number of partitions that we partition the range of each entity into. And N is an assumption I made about the population about the world. I assume that there are 10 billion people in the world. There are actually 8.1 billion. Okay, so it's a very generous estimate. In the last column, you have a 1 in X chance listed, and let's just pick 6 here for example. A very conservative estimate here shows that for 6 levels of quantization, the chance that 2 people in the world in a world that is populated by 10 billion people will have the same voice is 1 in 346 trillion. So this is mentioned in a paper which is under review. Human voice is unique. It will come out soon. And this is not all. We haven't accounted for the dynamic variations in voice that happen every day, every minute in our voices. Our glottal airflow dynamics, the dynamics that produce our voice, is modified by external influences, cognitive changes, physiological changes, environmental changes, drugs, diet, whatever. Lots of influences have been identified. So it wouldn't be very far off the truth for me to say that the chances of 2 people having the same voice in this world are less than 1 in 1 trillion. In fact, this is a very generous estimate, a very conservative estimate. So human voice is unique, and it can be proved to be unique. Voice is also a powerful biometric, and we all know it carries information about the speaker because we make judgments about other speakers from their voices all the time, and oftentimes we are correct. Oftentimes we are also wrong. So it carries information about the speaker, the static kinds of information, but also about what is happening to the speaker at the time of speaking. You are influenced by many factors at any given time, and your voice changes subtly in response to those factors. But the burning question here is, where is this information? Where does this information lie? And in order to look for that information, we can examine the voice signal from many lenses. I'm going to look through only one of the many possible lenses, and that is a glottal flow waveform. So let's start with the shape of the glottal flow waveform. I'm going to explain what the GFW is as we go forward. We're back to the pure tone, okay? An infinite sinusoid of 400 hertz, which sounds like this, all right? Now, let's look at a deviation from it. This is a sawtooth wave. Its frequency, it's also 400 hertz. It's also infinite. And it has 400 cycles per second, but because it is not a sinusoid, you will see a harmonic structure in the spectrogram, as you see below. And it's a very clean and nice harmonic structure. Now let me start distorting this wave. Here's a wave again. With a duty cycle 50, let me change that to 75. By changing that to 75, you see that the energy distribution among the harmonics in the spectrum changes, right? I change it to 90, the energy distribution changes again. I distort the sawtooth a little more. And now you see the energy distribution is different. With more distortion, it changes. Now it's starting, I'm distorting it temporally, differently temporally, and you see temporal differences in the energy distributions in the spectrogram. Now, what has all this got to do with the human voice? Here's how it has a bearing on it. So, for that, we have to very briefly consider how we produce voice. In order to produce voice, we let air out of our lungs. The air comes out of our lungs and it passes through vocal folds in our larynx, which is our voice box, which you can feel in your neck. And in the larynx, we have vocal folds or vocal membranes that vibrate to produce sound. And the sound that is produced in this manner is a very small sound that resonates in the chambers of your vocal tract, the oral chamber, the nasal chamber, the cavity behind the oral chamber, and so on and so forth. So if you look at the fine details, if you look at the anatomy of the larynx, you will see that we have, as I mentioned, two vocal folds that vibrate in response to the air pressure that comes out of the lungs. The motion of these vocal folds is mediated by 6 very intricate muscles, which can move these vocal folds and change their shape in different ways. Now, when I speak, for example, my pitch is around 200 cycles per second, or 200 hertz, which means my vocal folds are vibrating at the rate of about 200 hertz, or 200 are vibrating 200 times per second, and my glottis, which is this area here, is opening and closing 200 times per second. Muscles cannot mediate this. This is self-sustained motion of the vocal folds that is set into that is set into motion by a very intricate balance between in the aerodynamic forces that are created when the air comes out of the lungs. So it's a very, very complex process, but let us look at a recording of it. Here is what is called an electroglottogram. And if you look at the central graph here, it is the vocal fold contact area. So when we produce sound, voiced sound, the vocal folds are opening and closing and opening and closing. So this shows the contact area of the vocal folds. When it is high, that is, the glottis is closed, the vocal folds are close together, then the airflow volume, the glottal airflow volume is less. And when it is low, the glottal airflow volume is high. And this change in the glottal airflow volume, up and down and up and down, is roughly a sawtooth wave. And the shape of this sawtooth wave, as you can see, is it's not very smooth. Every kink in it, everything about it, it's upslope, it's downslope, its shape, its angle, everything is dependent on something intricate in your vocal production mechanism. If you just look at the physical properties of the vocal tract, much of that structure reflects these properties. We have, from speaker to speaker, there are differences in not only physical properties of the vocal tract, but in the every aspect of the vocal production mechanism. Physical properties are everyone has different skeletal proportions, different tissue elasticity, different muscular thickness for their vocal folds, and so on and so forth. The list is very long, and this is not a complete list. Because of these changes, that sawtooth-like wave that you saw, which is called the GFW, its shape is different. And because its shape is different, the energy distribution in the spectrogram is different, and it is temporally different when humans produce speech. Here is an example of Michael Jackson's song.
Oh, evening sky, somebody's broken heart, and a washed out dream. They follow the pattern of the wind, you see, 'cause they got no place to be. That's why I'm starting with me. I'm starting with the man in the mirror.
These patterns that you see, these complex patterns, are a result of changes in that sawtooth waveform that I showed you, the glottal flow waveform. There's a lot of information about the speaker in this representation. There are, of course, other representations that you can study, but extracting the plethora of information in this representation alone is huge. It's a challenge, but at the same time, it is a very enriching exercise. So that's one aspect. Let's look at the resonances that are related to the glottal flow waveform. Here again are the pulses, the air pulses, as the glottis opens and closes. They are called the pitch pulses. And you can see individual pitch pulses over here. This is time, this is frequency. And what you notice here is not only every little jet stream different in its characteristics, over time, there are some frequencies, this y-axis is frequency, that some frequencies that have a higher energy than the rest. These are the resonances of your vocal cavities. These are the resonances of the vocal tract. They are called formants, and they are labeled F1, F2, F3, F4 in this figure. And these resonances are very closely connected to the shape and the dimensions of your vocal chambers. So in the example that I showed you of the countertenor, for example, he spoke in his normal voice, then he went into a countertenor mode. The resonances are very dependent on the actual shape and of his oral chambers and the nasal chamber, his vocal chambers. They do not really change, and you will see it in the spectrogram, which corresponds to this little snippet from that performance.
No, I'm a countertenor.
So there's his normal voice, there's his countertenor voice, and you see the high energy. Generally, the formants are in place through both.
No, I'm a countertenor.
Now, so these resonances carry information about the shape of your vocal chambers, and the shape and dimensions of your vocal chambers are very intricately connected to the shape of your skull. They're defined by the shape of your skull. And the shape of your skull, of course, defines your face, defines how you look. So it is possible to reconstruct faces from voices. My student Yan Dong Wen finished a PhD thesis in 2022 on this subject. His thesis is titled Reconstructing Faces from Voices. He did very good work, and I do recommend you look at his thesis for more information. That technology at that time was also used by Winterman Thompson and HSBC in a real-world application. And here's a snippet of that real-world application.
What if we could reveal a fraudster's face and have them teach us their tricks? We used an AI that predicts a fraudster's face by analyzing their voice recordings. Each voice has a unique fingerprint that correlates to features like size of jaw and shape of nose. In a world's first, this AI analyzed fraudsters' voices and generated their portraits. These digital reconstructions were then brought to life in a series of tutorials.
There are many faces of fraud, and we can fake anyone or anything. Get to know us and learn our tricks.
This was an ad campaign commissioned by HSBC. They were trying to educate people about fraudsters. Anyway, so this is one lens out of many, many lenses. Intricate changes in the GFW and other representations can indicate many, many, many different kinds of human conditions. Intoxication, diseases, drugs, many others. So all of this has huge implications in diagnostics. But the question, again, is how do we derive these changes? That requires a lot of research. So there are many ways in which you can approach the problem. One of the ways, which is outlined in my student Wenbo Zhao's thesis, Computational Models for the Forensic Analysis of Human Voice. He finished this in 2022. Is an analysis by synthesis method, which very briefly, it uses a set of mathematical models which can generate the glottal flow waveform if you give them the right parameters and start them off in the right way, initialize them in the right way. These bioparameters, he showed in his thesis that these bioparameters can be estimated from recorded speech. And so when you have recorded speech, you estimate the bioparameters, plug them into these mathematical models, and they generate the equivalent of what might be the actual glottal flow waveform of the speaker. And then you can study the characteristics of the glottal flow waveform. So this is a snippet from his thesis. So this is the mathematical model that you can see here. It's it's one of the simplest mathematical models. It's a set of coupled nonlinear partial differential equations, which have variables which correspond to the motion of the vocal folds and parameters that relate to the physical properties of the vocal tract. And when you solve these, this dynamical system iteratively, it exhibits all the behavior of high-dimensional nonlinear coupled partial differential equations. Dynamical systems like this are more likely to be in chaos than otherwise, and this comes from chaos theory. So some of the interesting behaviors that chaotic systems or dynamical systems exhibit are shown here. These are plots of their trajectories and what is called their phase space. And you will see many different kinds of shapes that they create. These trajectories create. Here's a torus, here's a fixed point where no matter where you start from, no matter what your initial conditions are, the solutions converge to a point. Here the solutions keep going in a toroidal fashion. Here's a strange attractor. The solutions are confined to a closed region of the phase space, but they never intersect. They never cross each other. It's called a strange attractor. Here's a limit cycle and so on. So if you do this analysis for voice, and especially voices that are affected by different known conditions, and look at their the plots in the phase space of the dynamical systems that generate the glottal flow waveform, you can see very clear partitions. So I'm going over this very fast, but in the experiment that Wenbo ran, he took normal voices and voices affected by neoplasm and phonotrauma and vocal palsy, and they segregated out into clean areas of the parameter and variable space of the system. And here are the plots that he obtained. These are the actual estimated vocal fold motion, or the GFW plots for people affected by these 4 different conditions. And you can visibly see the difference in the trajectories. So these differences so we applied this to the task of detecting COVID when COVID hit in 2020-2021 timeframe. And here you see the differences between the voice of a person, or the vocal fold motion oscillations of a person who has just been diagnosed with COVID, early COVID, and the change in that motion when that person has crossed 7 days of being infected with COVID. So this is mentioned in the paper listed below in this slide. So a lot can be done from this approach, but there are many other approaches that we can take, and I'm going to go into one of those going forward. Around 2019, I wrote a book called Profiling Humans from Their Voice, and I put in some information. A lot of my understanding and a lot of the information that I put in there has evolved from that point on, but there are some chapters in this book that are actually useful if you're curious. So what has happened now is that, of course, we have AI. It's a much more powerful tool than the traditional signal processing methods that we have earlier. And so another approach that we can take, it was also mentioned in the book, at least some version of it, is the approach of joint biomarker discovery and classification to uncover this kind of information. And this is all based on a hypothesis that I made. And my hypothesis goes like this. It allows us to search well beyond human judgment, audition, vision, and cognition. Basically what I say, if a factor affects your mind or body, voice production is a physical process, it's a biomechanical process, but equally it is also a cognitive process simultaneously. So if a factor perturbs any part of that process, if it affects if it exerts an influence on your mind or body, and if a biological pathway, an actual biological pathway, can be traced from that influence to the vocal production mechanism, then there must be an influence on voice. And if there is an influence on voice, then it must be discoverable. So there are 2 parts to it. One can be explored through cytogenetics and genomics. If something perturbs you, if you have a cup of coffee, metabolic pathways are unleashed in your body. Do they connect eventually to your vocal production, the pathways that control your vocal production mechanism? That can be traced. The second part is, if such a pathway can be traced, then there has to be an influence on the voice. It doesn't matter whether we can perceive it or not. There has to be an influence. And if there is an influence, then we should be able to design AI mechanisms to discover that influence or those signatures. So as you can see, this is a very useful and powerful paradigm. So genomics and cytogenetics on one hand can link different influences on humans to voice. The connection of everything to voice can be inferred. And if it exists, it can be discovered. I wrote a paper about this in 2023. It is listed on this slide. And if such a connection is established, now we no longer have to depend on our human observation or perception. If it is established, then you can put together a simple mechanism for biomarker discovery. This is a very simple mechanism. There are lots of other variants possible, of course, where you have all of this as a neural network-based system, and there's an embedding space where you evolve a vector, where you actually construct a vector. You allow the system to construct a vector that satisfied the many constraints that you want to satisfy in order to discover that influence or that signature. The vector itself will be the signature. So that was a very, very, very sweeping and broad description of a biomarker discovery mechanism. I have a patent on it as of now. So anyway, the implications of this are huge. So if we can, in a principled way, predict which of the 30,000 plus different diseases that are known to affect mankind are likely to have an influence on voice, then you can design AI mechanisms to uncover those influences. And through this method, you can come up with diagnostic aids that can identify all kinds of diseases from voice, not just the ones that we know are influence voice. So it has the potential to, and other than diseases, it has a potential to identify physical, physiological, psychological, cognitive, neurodegenerative, lots of even genetic traits from voice analysis. And it has a potential to also identify personality, emotion, behavior. You've seen lots of work in paralinguistics that tries to gauge a person's emotional status, personality status, etc. from voice. All of that can be done, is being done. We can infer a lot of biorelevant information from voice. All of this information that's listed here and more. We can infer environmental influences, other external influences, what kind of drugs you've been taking, what is your diet, what have you been eating or drinking, whether you're intoxicated or not, many other things. And this also has implications in security. But then we come to generative models. And the game has changed. It doesn't stop there. It was already very powerful until the last slide, but it has become even more powerful. The game has changed. Firstly, in generalized audio models, analysis tasks can be cast as generative tasks. Let's take human voice profiling, the science of extracting information or biorelevant parameters about the human from their voice. Let's take that. Here is what a generative AI system can give now. And this is now a generative task, an analysis task that is cast as a generative task. Here's the output of Colombo, a system that we reported last year or something. The audio features a male speaker, likely between 36 to 45 years old, with a Caucasian ethnicity, speaking in a deep resonant tone, characteristic of a 36 to 45-year-old American English native speaker with a medium build and height, speaking in a native American English accent. He has just had a cup of coffee and is happy at this moment, so speak to him in a normal tone. So it can just go on. And these systems are now also capable of reasoning. And one of the types of reasoning that is being infused and is also coming up as an emergent property of these systems is chain of thought reasoning. And here is an example of what that implies. So if I have a question like, can you write a whole haiku in a single tweet? And if I give this as a prompt to a system, it would give you an answer, yes or no. Now, it could also reason through it to give you an answer. It could have a process internally which might go like this. A haiku is a Japanese 3-line poem. that is short enough to fit in 280 characters, and therefore the answer is yes. So this is chain of thought reasoning. It can be externally infused into the systems, but it is also emerging as a property of large systems, without, even if they are not explicitly taught to reason in this manner. So what else is happening? The other aspect that we need to consider is that a single generalized audio model or an audio LM or language model can do everything. Every task that humans can do at phenomenal speeds, at massive scales, with much greater accuracy. And when I talk about all tasks, here's a partial list of audio-related tasks and speech-related tasks that we do as humans on an everyday basis. So a single model can now be constructed to do all of this. The burning question again is, okay, the machines are able to do all of this. Can they? And they're able to generate speech, but can they generate the biometric information in a speaker's voice as authentically as the natural vocal production mechanism does in a human? Let's examine that question. And we'll also examine generative AI models for audio in a little more detail. So let's first do that. Okay, so over time, from 2016 to 2024, there have been lots of voice generation, voice cloning, and style transfer models proposed in the literature. And they have only gotten better and better and better. By the time we came to 2024, we had 11 labs and Meta Voice and Open Voice is especially good model, Valley 2, and so on and so forth. And I'm going to show you some examples from these models. So here's a very interesting example. In 2024, President Trump, who was not yet president at the time, was campaigning in Pennsylvania, in Butler, Pennsylvania, and somebody shot at him. This photograph was taken at the time he was shot. And just a few hours after this, a song appeared on YouTube in Donald Trump's voice, singing about how many people, many men are after him. Listen to this song. The music, the gunshots, everything in this song are AI generated.
Wish there for me, blood in my dog and I can't see. I'm trying to be what I'm destined to be, and he's trying to take my life away.
Perceptually, this is exactly Donald Trump's voice. Here's another example. This is a real voice of Elvis Presley, in 1957.
Here is Elvis. You ain't nothing but you ain't nothing but well, you ain't nothing but
Elvis died in 1977. This was created in 2023, 2024 timeframe using those models by Metaphysic. This is entirely AI generated, and I'll leave you to guess how this was done. It's very, very simple.
Thank you. Thank you very much. It's yours an honor to be here with you all on America's Got Talent. I'd like to thank Tom, Chris, and Metaphysic for having me here tonight. I have to tell you, we're going to do a couple of our biggest records for you now. This first one is a tender love song. And as a great philosopher once said,
You ain't nothing but a hound dog, yeah, crying all the time. You ain't nothing but a hound dog, yeah, crying all the time. Well, you ain't never called it when you're waiting on friend. Well, this ain't what's fine. Well, that is the line.
Okay, could you guess how this was done? Any answers? All right, so there are people on the stage and there are cameras trained on their bodies. So the below the neck, it's the actual body of the person who is performing on the stage. The face is face swapped using simple, I think, GANs. And the audio is cloned. This is Elvis's voice. That audio, this is voice transformation. This is a voice transformation system that is transforming the person's voice to Elvis's voice. And the audio is lip synced to the face. Very simple. Here's another example.
Look like an angel. Look like an angel. Walk like an angel. Talk like an angel. But I got one. You're the devil in disguise. Devil in disguise. You fool me with your kisses. You cheated on the ski. And I don't know how I look like an angel. Walk like an angel. Talk like.
Okay, that was just to give you a break. Okay, how does it work actually? Let's look at it. It's really very simple. In concept, it's very simple, not in implementation. Okay, so how does it work? I'll kind of try to get this across using a very simple example. I give you a string of characters, which looks like this, okay? And I ask you to complete the sequence. Immediately, you know what the last character is going to be, what the next character is going to be. It's going to be N, Abraham Lincoln, right? Now, if I give you this character sequence, you're still going to be able to complete it, right? You would complete it like this. If I give you this sequence, and I don't give you any other information, and I ask you to complete the sequence, you can't. I mean, there are many possible completions, and you don't have enough information as of now in this. You don't have enough context. So some context could help. So if I give you the context, American presidents, then you know immediately how to complete the sequence, right? If I change that context, the Bible, the sequence that you come up with, the sequence that you generate is going to be different. If I give you yet another context, magic, the sequence is going to be this, abracadabra. So the context is very important in generating what comes next in this sequence. So in each case, what we did was we came up with the most appropriate completion given the input, which was the partial sequence and the context, right? So this is exactly what systems, the neural systems do. You give them an input here, you give them a context of some kind. We have to figure out what is in this green box out here, and they generate a completion or the next expected output in the sequence. So we need to computationalize the process. We need a block that accepts one or more inputs and a context and generates the most appropriate output. So the question is, what is in the box? How does it obtain all the knowledge required to generate the right output? Where does it store it? How does it use to generate the right response for the context and input? And how do we determine what is most appropriate? So let's look at this, the one highlighted in navy blue here. How does it, so what the question is, how does it obtain all the knowledge? Where does it store it? Okay, so this is that block. So transformers were introduced in 2017, and a transformer is a neural architecture that will pay attention to the input, and it will pay attention to the context, and it will pay attention to its own recent computations if it starts generating something to generate the next output. And this answers the question, how does it use a context, right? next part of the question, where does it store it? For this, we have this part. It's a multi-layer perceptron, a feed-forward network. It includes components with a large number of parameters, which store its knowledge in the form of weights, and it uses it to determine the right outputs. Now, all transformer architectures are some or the other variant of this. The basic thing is the basic concept is very simple. The entire model can be trained from large amounts of data, and that answers the question, where does it obtain the knowledge from, right? You give it examples of the kind of data it is supposed to generate. So this architecture shows you it's a very simplified block of a transformer. The actual model stacks, so the actual transformer models that are used in the literature have stacks of these blocks. So in the current literature, you will see that there are many variants of this basic architecture. You have, generally the complete architecture is an encoder and decoder architecture. I'm not going to explain that. It would take a long time to explain, but it's again, this simple concept implemented in that way. There's an encoder that encodes the knowledge, and there's a decoder that generates the output. So the encoder-only models, we have encoder-only models. We have models that use only the decoder. There are models that use encoder-decoder pairs to convert between different modalities. So many further modifications to increase the memory, context efficiency, and so on and so forth exist. There's a lot of literature out there, but the basic answer is in this, what is this green box? It is a transformer. And it is a very simple conceptual mechanism to assimilate knowledge, pass it forward, use it to generate the next output. Now, the next question is, how do we determine the most appropriate output? What is the most appropriate output given the context? How do we determine that? Well, there are mathematical ways to determine it. So there are the two ways that are most widely used are mentioned here. In one definition of appropriate, we mean most likely. So we select the response, we implement the math so that we can select the response R over here that has the highest probability given the inputs. You can formulate this problem and you pick R such that probability of R given the input and context is maximum. And that will lead to a maximum likelihood training. In a second definition, the definition of appropriate is most aligned to human expectation. So in this, you pick R so that human evaluators are likely to rate R highly. And this leads to what is called RLHF. It's reinforcement learning based on human feedback. There's lots of literature about it. So the inputs and output and the context could be anything. The input could be an image. Your context could just be a command. You derive some representation of the image, some representation of the command, project it into the transformer's internal space, and then it learns to generate the output that you need. So here, if I give a context or a prompt, draw a colorful picture of a harlequin dancing in a field on a sunny, beautiful day in a beautiful village, out pops the set of 4 pictures. This is the output of GPT a few years ago, actually. So it basically maps it to a trajectory in the image space and gives you the corresponding images. How do audio models generate audio? How is speech generated? That's the key question in this context, in the context of this talk. The architecture remains the same. You're going to give an audio signal as an input, and that's going to be converted into some representation, for which we use a tokenizer, which is also a neural network that transforms this into some representation. You're going to give it a context. You're going to have a transformer model, and the output of it is going to be a spectrogram or something like a spectrogram, which can be then sent to a vocoder. A vocoder is a mechanism that can take a spectrotemporal representation like this and convert it using signal processing, or nowadays signal processing neural techniques. You could use a neural vocoder to convert it back to a speech signal. The mechanism is as simple as this. Now, what are the future capabilities of these models? Can they improve indefinitely? Well, we're talking about models where any kind of multimedia input generates outputs, and that output is rendered into actions. And the action that we are interested in is producing speech. Let's look at some actual audio generative models a little more closely. I know we are running out of time. It's going to end very soon. So the field of audio language models for audio-centric tasks is growing exponentially. It is over time. You can see this slide gives you some names of some key models that have been proposed in a period of 4 to 5 years. Now, when you talk about generative audio models, there are lots of them out there. How do we categorize them? From the lens of optimization, I can think of a three-part categorization. You can categorize them into diffusion models, language models, and agent workflows. So let's quickly take a look at what these are. Here is a diffusion model. Looks complicated, but it's really very simple. It is based on nested variational autoencoders. Basically, a variational autoencoder will take some representation and learn to generate the exact same representation through its internal encoder-decoder mechanism. And I think all of us are familiar with this, so I won't explain it much in detail. So it uses a VAE to compress or decompress the spectrogram into or from, at this end, encoder end, from this end, a low dimensional latent representation. And that low dimensional latent representation isn't just a simple representation. It is a latent model that is a UNet. It's a UNet denoiser. It's called a UNet denoiser. Also a VA trained with cross attention with the text representation. Text is also given to it at this point. There's a transformer that generates the latent representation we need here in order to get the spectrogram out of the model. So this mechanism eventually ends up learning to generate spectrograms with very high fidelity. That is the strength of diffusion models. And then at the end, you can take a vocoder and generate here. You can pass the spectrogram generated to a vocoder, and it will generate the audio. In this case, in this paper, which is the title of which is listed here, they take a neural vocoder. It's called a hi-fi GAN in their paper, which converts the latent spectrogram into a 48 kilohertz waveform. You can get as specific as that, but generally diffusion models work like this. Then there are language models. Here's an example of CLAP, which stands for Contrastive Language Audio Pre-training. And this is also very, very simple. Basically, you're taking the context, which is your text. This is a text. It is encoded by a text encoder. You're giving it the actual audio, and it is encoded by an audio encoder. And in the model's latent space, you compute what is called a similarity matrix by taking the dot product between the two. And then you minimize, in the training process, you minimize the symmetric cross entropy between the two. And once that is done, the system can be used for zero-shot classification. You can give it some new testing audio, and it will find out what label should correspond to it. Here's an example of another kind of language model. It's called Pengy, and this is more sophisticated than the CLAP model. It can take a prompt and any kind of a prompt and either complete it or give you an answer. For example, if you give it this emotion is, it completes it as happy. What type of animal is making the light sound in the background? It is a bird. It's giving you an answer. How is it doing it? The architecture doesn't change. It still remains the same. You have a setup here that can transfer the knowledge. You have an audio encoder. You have a text encoder. One acts as a context to the other. Both of them are projected by some mappers into the language model space. These two are independently encoded, and the projection is a prefix, and this is sent into the transformer model. and it learns to generate the appropriate output. It's very simple in concept. This is I'm not going to explain this, a more sophisticated version. I wouldn't say more sophisticated. It's a different version of the same basic concept. You have all the way up to so this is the pre-processing, this is a multi-scale transformer, this is a predicted audio sequence, and this model, Uni Audio, is capable of performing many different tasks: speech enhancement, voice conversion, audio generation, so on and so forth. And for it, in this specific implementation, it uses specific local transformers that do a better job at generating each of the kinds of different outputs that you want. Wavecraft is a completely different category. This is a human language model teaming kind of setup or categorization where you use a language model to generate code that will allow you to do some sort of editing or make some changes or understand your audio better. So basically, the user gives an audio, uses a language model, and that is then vetted by audio programmers to give a computer program that will do the tasks that you wish to do. And so I'm not going to dwell much on this category because I don't think it is that interesting. It is more on the engineering side. So very quickly, we are coming towards the end. Let me answer a few questions. How capable are these AI systems today? We're going to talk about the kind of voices they generate, but in general, how capable are they? So they're very pervasive. They are very capable. Almost all scientific problems today can be cast as generative problems, all the way to theorem proving, right? They're superhuman already in their capabilities. They're millions of times faster. Their reasoning capabilities are coming up. They're more informed than any human. They're trained on vast amounts of knowledge, more than we as humans assimilate in our lifetime. What lies ahead in the future? Well, we know that embodied AI is coming. These language models, these powerful systems can be put into mobile robots of different kinds of embodiments. And they can then learn to do real-world tasks, which with much greater accuracy and finesse and skill than they ever used to be able to. So that's coming. And then we talk about escalating power. That will be an issue in the future. Our architectures are becoming larger and larger because we want the tasks to be done better and better and better. And the only ways we see forward these days is by increasing the number of parameters, by making more complex architectures. There is a group of researchers who are researching the possibility of going in the opposite direction. But by and large, we are going toward larger architectures. And we're also beginning to see quantum computing come up. And if that is applied to classical computing, that is going to allow us to come up with models that have unimagined capabilities. I'm going to talk about that in brief going forward. A little bit. This is a very fast-paced and broad overview. So to the question, how complex will AI systems become? If we assume that AI systems will continue to make a positive difference to human societies as they are, leading to an ever-increasing uptake, as is happening today, if we assume that larger architectures are more efficient, not efficient, but more powerful, then we know, or we can assume safely, that larger architectures will continue their trajectory in giving us better results. And they will also be exhibiting more and more emergent properties. I'm not talking about those right now, but that's another thing that's driving the size of these models. They are exhibiting very interesting emergent properties that we want to explore further. For example, are these models ever going to become self-aware? That's one thing. So assuming the fundamental learning mechanism remains the same and we keep growing these architectures, we are for sure energy doomed. Okay. If we keep growing the AI, we are going to run out of energy. And the depiction of that is given by, this is the output of an AI system that is trying to show the enormity of the expected energy usage by AI systems in future. So let's get this down straight to have a reference, a sort of an idea of where we are going. If we talk about one average AI query, then that is equivalent to using a few seconds of light bulb in energy consumption. It uses about 0.8 to 3 grams per query of carbon, or it causes CO2 emissions of 0.8 to 3 grams per query. It is equivalent, one single AI query is equivalent to hundreds of Google searches, and longer queries increase consumption. Where is all this coming from? It's the sources written at the bottom of this slide. So these statistics come from there. If you look at cryptocurrencies for comparison, Bitcoin, for example, I mean, you need to mine cryptocurrencies and you need a lot of computing for that, compute power for that. Bitcoin mining consumes about 90 to 120 terawatt hours per year globally. AI, on the other hand, it's going into data centers and is a growing part of these data centers these days, is consuming about 300 to 400 terawatt hours globally. And data centers that are exclusive for AI are coming up. So there is an exponential growth underway. We haven't even factored in embodied AI. We're just looking at data centers when we talk about these statistics. So we're going to run out of energy. And so the solution to this problem has to be thought about right now. And the solution is simply not to keep growing the architectures, but to reduce the computational requirements of these architectures. And how can we do that? We can do that using quantum computing. And I'm going to give you just a glimpse into quantum computing before I go to the final topic. And that will end in a few minutes, I promise you. Quantum computing. Why are we going into quantum computing? Why are we thinking about it? What is the main idea behind it? Why is it so powerful? To understand that, let's just consider this. A 3D space. Here's a vector that I'm showing in a 3D space. And let's consider the classical concept of space that we deal with every day. So a 3D space, and here's a vector in that space. Now, if the axes of this 3D space were bits, they could represent 0 and 1, right? And so between these, the bit combinations that they could represent are shown here. They would be the corners of a cuboid in this 3D space. And every vector, every definable vector in this 3D space would be one of 8 possible vectors that are defined by these points, 0, 1, 0, 1, 1, 0, all these 8 combination of 3 bits, okay? Now in this space, if we had an unknown function, f of v is the vector, and I asked you to evaluate this function, tell me what this function is, you would have to evaluate its outcome on all of these 8 vectors, right? So we're talking about a classical space where each basis is a bit, which is the space in which our current computing systems work. In that space, of course, 3 is not the small number that we use for computing. We use a lot, many more bits for computing in our computers today. So if we had n bits, and if we had an unknown function f of v, to find that function exactly, we would need 2 to the power n function evaluations in the classical space. The question here is, can we construct, and that's a lot of computation. So can we construct a space where we can find this function in a single function evaluation? If you think about it, turns out, yes, we can. And for that, we have to change our mindset. We have to change the way we think about space. We must now think about a space where not just each bit, but each bit combination is a basis for that space. So now we're talking about, with the 3 bits that we were talking about, we are talking about an 8-dimensional space. I couldn't draw it. I didn't know how to draw an 8-dimensional space. So this is not a true representation. But each of these is an orthogonal axis in the space. And in this space, if we had n bits, okay, let's say, so any vector in this space in the first place would be a linear combination or a superposition of all these axes or bases, right? So any vector v would be some combination of a times one axis, b times the value of the other, and so on and so forth, right? A, B, C, D, all of these are probabilities, and the bit combinations are what define our new bases in this space. These are qubits, right? So if we had a vector v in this space, then in order to find that vector, or find the exact function f of v of that vector in this space, if we could define that function as just a rotation of this vector v in this space, then if we had the function f of v and we recast it as a rotation transform that would rotate v to w in this space, then with a single observation, we could tell what the rotation was, and this would fully characterize the function. So one computation would be all that would be needed in this space. But the big question is, how do we define these bit combinations? How do we define the equivalent of a bit that can be 0 and 0 and 0 at the same time, right? So how do we construct this n-dimensional space? For this, we use quantum phenomena to create the qubits. And each qubit here, each basis is a combination of these 3 bits that can be both 0 and 1 with some probability at the same time. So I know this is a little confusing because I'm not explaining it too much in this lecture, but this is the basic idea behind it. Constructing the qubits is not easy this way. Just measuring quantum phenomena that can be 0 and 1 at the same time, or sets of those that can be put together to form these combinations of zeros and ones at the same time is very difficult. And in order to do that, it can be done, but in order to do that, you need computers that are made of gold. This is a picture of an actual quantum computer, and I kept at very low temperatures, 4 degree Kelvin or something, and so on and so forth. The hardware is catching up with the math, but the math is already there. And if we use this kind of computation in AI systems, then computation would be greatly accelerated, power consumption would be greatly reduced. So assuming we solve all these problems, what we are looking at is embodied AI will be orders of magnitude more intelligent than we are. We will have information teleportation that comes from quantum computing. We can actually transmit information without having any physical connection whatsoever between 2 entities across the globe. Question is, will they be sentient? Again, curiosity. We'll see what happens. Now, an ending note. What will the voices of these embodied systems be like? And this is the final question I promised I would answer in this, or try to answer in this lecture. And let me bring you back to our world by playing you some voices, real voice, imitated voice, human-generated voice, or human-cloned voice, and AI-generated voice. And the first one is Michael Jackson's voice. That's Michael Jackson's voice. This is an impersonator. Human beings are good at cloning speech. This is entirely AI generated.
You breathe, and every moment sings a harmony no one else could bring. The way you move, it slows down time. A rhythm perfect, fine with mine. Hold your hand, the world's complete.
Okay. Perceptually, the voices seem fantastic. Of course, the human voice is good, but the AI-generated voice seems almost exactly like Michael Jackson's voice. Let's look at these voices closely. In this spectrogram, the first half or so is the real voice of Michael Jackson. The second half is a snippet of the AI-generated voice that I just played. And what you see here, I don't know if all of you can immediately see the differences, but they're significant. The spectral holes are gone. There is a face that is reflected in this voice. The spectral holes are a result of resonances, anti-resonances produced by your nasal cavity interacting, the resonances in your nasal cavity interacting with the other resonances in the vocal tract. Not there in this AI-generated voice. The AI-generated voice does not have a face. There are many other differences. If you look carefully, you can see there are many inconsistencies. We don't perceive them, but they are there in machine-generated voices. So machine-generated voices and human-generated, even this person's voice has a face, right? Not so the human-generated voices have a face, not so the machine-generated voices. What other differences exist? I'll point out a few. There are inconsistencies in how energy is distributed in the higher frequencies. Here on top is a spectrogram or the spectrum of the real voice of Michael Jackson. Here is the spectrum of a snippet of the artificially generated voice. And you can see that the AI system never runs out of energy as it is singing or speaking. It just keeps going and going and going in the frequency space. It has energy to distribute in all frequencies. Conservation of energy is not followed here. There are other things here that I could point out, but suffice it to say that machines, because they are not correctly informed up to this day, are not able to really produce voices that are like human beings. In fact, here is an example. This is again a snippet of Michael Jackson's voice on the left, a snippet of Michael Jackson's voice on the right. It's more of a close-up. You can see the differences. The spread in the higher frequencies is just completely all over the place. But this is equivalent. This holds a face. It could be Michael Jackson's actual face. This holds the equivalent of a face that the best AI system out there, for which I paid a lot of money. My student talked me into paying money to that, to subscribe to that system, generated for me. Here is a conversation between that student and myself. He says the model will perform much better when presented with few short in-context prompting examples. So I prompted this system to generate a diagram of the human vocal tract. And this is what it generated. This is what I would say is equivalent to what is in this, right? And then I sent it to him, and this is his response. The relative sizes are off in this image. So I find that really funny. But on that note, I would like to stop here. I think I've run over time. Thank you very much for listening. And I'll take questions now.
Thank you. Thanks so much, Rita, for such an interesting, very insightful talk. A lot of topics covered. So I think that everyone could get a grasp of everything that's going on in the field of voice recognition and also how can you process efficiently these models. So very interesting. Thank you so much. Okay, I think we have a few minutes, time for a few questions. Not very much because we've passed a little bit of
I
our.
went over time. I'm so sorry about it. I had
Don't
not
worry
time.
about it. Yeah, I couldn't stop you because it was such an interesting talk. So I wanted to, give you the space that you needed. So we have a few minutes for talks. So for questions, if anyone wants to ask something. Okay, we have Viviane with her hand raised. Viviane.
Hi, thank you. Thank you so much, Rita, for this very interesting talk. I learned a lot of different facts about voice and how to use it as a biometric. I think I have a very simple question. So, in order to be able to identify a person, a system would have to be, an algorithm would have to be a little bit flexible to say, like, to identify that this is Michael Jackson with a cold, this is Michael Jackson with COVID, this is to all the different things that could affect the person's voice. And yet it would have to be smart enough to say, to distinguish between all these facts and someone trying to impersonate Michael Jackson or an AI trying to emulate his voice. So is this already possible, like to account for all the different things and still be able to attribute the voice to the right speaker?
Yeah, that's a very, very pertinent question, and it is a challenge in human voice profiling. So for this, we study the voices of impersonators, and the goal, it's a big challenge in the field, because you're right. If we are not able to discriminate between real and impersonated voices, then we would be making wrong conclusions about the person. So we try to identify which aspects of the vocal production mechanism are within the control of the impersonator. These are the aspects that impersonators use to mimic other people's voices. We explicitly do not base any analysis on these aspects. We just leave them out. Right? And we focus on those aspects that are not under voluntary control of the impersonator. And so that's how we can tell. And the fact that an impersonator may be varying some aspects of the voice and not able to vary the other aspects also introduces inconsistencies in many domains in the signal. So you can actually study those inconsistencies, and this is not perfected yet, but in concept, in principle, you can, and you should be able to say that this voice is an impersonated voice. It is not real voice, because there is no continuity in the way we expect in a natural voice signal, right?
Great, thank you so much. Thank you.
You're welcome. Any other questions?
All right, do we have any other questions from the audience? Also from YouTube, if anyone wants to ask, you can just ask on the chat, and I'll pass it on to Rita. I have questions as well. I have more than one, but I think I have to email most of them to you.
Okay.
So then we don't take too much time here. But I had the question regarding when we work with visual models, we also use variational autoencoders for generating images, or for any other type of manipulation that we want to do. And these models, even the variational ones, which are still better in terms of overfitting, they are still very prone to causing hallucinations that we can easily detect when we see an image with more focused attention and a trained eye, let's say.
Yeah.
Do we have some kind of artifacts like that as well for image for speech generated
always
content?
Up until now, these artifacts are going to be present, because we're modeling a continuum. We're modeling a space, the space of the entities that we are trying to generate. So if it is faces, then we are modeling the space of human faces, right? and whatever is generated is the most appropriate entity from that space. It is drawn from that joint distribution, right? If we haven't, and when we are training, we're working in the digital domain with limited data. We are only sampling that. We only have some samples from that space. The rest of the space is guessed, right? Estimated. So we're not always going to be, because we cannot explicitly model that space. Whatever is generated has a likelihood of being wrong, right? So that will always remain. That likelihood will become smaller and smaller and smaller, but it's not going to vanish until the extreme is reached, where the system is exposed to every possible input and output combination that is available, right? Or that can happen.
I also have a very quick question in terms of forensics. Let's say you said that if we extract pictures like in the old way, right? We have a spectrogram, we extract pictures from it, like handcrafted pictures mostly, and we can find like ways to make like a fingerprint of our voice for trying to identify persons. How did you start to run these models for identification of a person with a version of that same voice from that person generated from an AI, let's say? Do you run tests like that?
Yeah. I mean, so again, this is still in its infancy. These models have not been perfected and all that. When we run these experiments, we definitely do have a controlled, data set for evaluation, right?
Yeah.
So we use that. It's usually it's always a held out set, right? So there's a training and a development and an evaluation set, and we use the usual scientific pipeline for validating. However, the problem is that validation is difficult in this domain because not a lot of data exists that is properly labeled for us to validate against.
I see.
Right? Yeah, there's in America, at least, it is very difficult to collect biometric data. So we don't have very many test sets. So while we have the know-how and the technology, we don't have enough data to completely validate it. So there's always the systems that we build are prone to errors, for sure. And so we have to vet it, vet these systems manually sometimes. We have to look at their output and we have to think, does it make sense from the perspective of what we know about voice, right?
Yeah, but it's also a form of validation. It's the supervision of an expert, right? It's something that we do in other types of research as well. So I think it was very interesting, Rita. I have some more questions. I will send them to you by email.
Absolutely.
Thank you so much once again. Thank you everyone for joining us. Just to let you know, our top audience here in the room was 16 people from what I could see. And in our YouTube channel, it was 41. So over 50 people already have already watched your talk. Yeah, and more will come because this will be recorded. So thank you once again for having this very interesting talk with us. And we wish you the best. And if you have any final words, yeah, thank you.
Yeah, bye.
So everyone, thank you for joining us. I will be ending the session now. Thank you once again, Rita, and I hope to see you soon once again in another talk.
See you.
Bye-bye.
Bye.